multitude of the microphones. All right, good. So yeah, so we are here to initiate a discussion on machine learning in astrophysics. Let's say specifically targeting simulations and theoretical modeling. And just to get started, let's maybe start with some questions. The first one. Have you used, let's say, machine learning AI in your scientific analysis? So who has so far done so? Please raise your hand. So I would expect it's, let's say, it's, quite a majority. I think it's like 90% or so of people, right? And that makes total sense, right? I mean, obviously, it's now everywhere. So who of you guys have used, let's say, the more modern approach? And this is like a more specific set of tools, so based on deep learning, let's say CNNs, GNNs, etc., and maybe have, let's say, trained them on GPUs. Okay, so I would say it's maybe down to about maybe 40% or so of the attendees. And now let me ask you, who of you has developed novel machine learning approaches or taking existing approaches but adapted them to a novel kind of problem? Okay, you have like 3-4 people. Okay, so clear, right? So it's obviously there are different kind of ideas of what machine learning is to us, right, and what it means to us, right? And let's say many of us are users, but some of us are also essentially active developers. Okay. So obviously there's a wide range of applications. Lucia and I, we just devised a list here. Obviously it's very incomplete. So maybe just let me just go over it very briefly. We can use it for like data analysis and data science approaches. For instance, in observations, you want to use it to, let's say, to classify galaxies, for instance, right? But there are many applications, of course. We just heard that we can use machine learning for inference-based approaches, to learn more about, let's say, astrophysical parameters. We can use it to build emulators. These emulators, of course, also be part of the inference machinery, but they can also be used for kind of other applications. And then there's also the idea to use, let's say, machine learning as accelerators. So we can essentially swap out, let's say, very expensive numerical calculations with machine learning, or with approximators that are based on machine learning. And of course, there's a huge range of techniques. I don't want to go into this, right? So we don't have time. All right. So that's the intro. Okay. Hope let's set the stage. And so now I really like the discussion session we had a few days ago where we had like 3 questions and we had these breakout groups. So I think Lucia and I would like to do this again. So we have here 3 questions, and we would like to you essentially look at your neighbors and you decide on one of the 3s, right? On the 3 categories. And we give you not too much because lunch is waiting. We give you like 3 minutes, okay? Or let's say 5 minutes, and then we essentially discuss the 3 questions. Okay, so please look at your neighbor. So pick one of the 3 questions, and then we're going to be back in 3 to 5 minutes from now.
We expect people, of course, to start the second part of the questionnaire. Okay.
Right, and so while you're thinking, I keep talking. I can maybe mention a little bit about the 3 ideas, right? So the first one is more about what you want to do, okay? In terms of, are there any specific applications? The second one is really more towards kind of simulations and SAMs. And then the third question is a bit broader, right? So if you think about how can we transfer knowledge from other fields, maybe to astrophysics.
Something about one of the good to keep it interactive. Because yesterday was done the food over there. I think people did not, I mean, there were always 2 or 3 people, they're always saying 2 or 3 people who were saying something, all the rest were not doing anything, basically. Especially the young people that completely not interviewing yesterday. So, really, so actually, do you want to moderate the session? You don't know. Yes, okay. Setting up. Okay.
I'm happy to share with you. So, yeah, so 2.5 more minutes.
So we'll go then and I will ask the first one, as you say.
Yeah, exactly. And I'm going to move somewhere, and then also I think Colin's going to help. So we're going to run around with the mics, and you're going to stay here and be the master of ceremony.
Okay.
Listen to.
Could be a couple of more minutes.
Yeah, so the question is for how long we do. So yeah, so 2 more minutes, and then we started, I think, 40 or something like this, and it should be, let's see, how long is discussion? 35 minutes actually. So it's not at 40, but we should do it a bit faster. So I would say we should stop probably 5 past or 7 past. So something like this. So 5 minutes each, essentially. But if you feel that there's a really super strong one of them, then or whatever, you know. But I think it's fairer to try to, because if people pick out, maybe the first thing you do is ask which question, you know, how many people, the first, second, third,
exactly.
and then we can see if there's one that was maybe not so popular, then we maybe skip it and, you know, say.
Which question you discuss more?
But of course the best is to discuss them all.
Maybe
Maybe you're right.
it's easier, right?
Yeah.
Yeah, so that means that we have about 5 minutes per question,
Yeah.
right?
Yeah.
More or less, 4 or 5 minutes.
Exactly, 5 minutes.
4 or
and
5
you can
minutes.
film and make it brighter. You can see
Yeah,
a clock
exactly.
in the corner if you want.
Because there's no more
Here
minutes.
is there a clock anywhere here? I don't see any. All right.
1 more minute, roughly.
30 seconds more.
30 seconds, okay. We do it the Swiss way. I was thinking of sending an email to Mir about the proposal because I don't want. I emailed Avishai just how he was. He told me that he's not feeling. He's not able to travel at the moment because he's not in good shape. So I didn't want to ask him, but we can write to Mir. Then he knows it.
Okay.
Okay.
Get started.
Okay, so I think time is out now. So it's now the turn for people to. Can you hear me? Okay, it's still. Okay, so it's now the turn for people to collect their thoughts very quickly, and we can start with. We can start with the first question. So, who wants to say something about the first question? Who wants to start the discussion from the first one? I hope that. Yeah, please.
So I think a big pushback and complaint I've gotten from a lot of folks in regards to even like more foundational machine learning models is the explainability aspect, right?
Mm-hmm.
Wanting to understand why models make the predictions that they do, and I think a lot of people maybe don't understand that there's a lot of tools now that sort of allow you to go into like trained either neural networks, decision tree models like XGBoost to sort of explain outputs in terms of feature importance plots or whatever it may be. I think like making aware of these tools is really important because we do live in the era sort of more explainable AI now, right? We're sort of outside of the black box picture. So I think for a lot of people that's a big obstacle or roadblock to why they might not try to approach using machine learning model for their problem.
So your point is the awareness of the new methodology, the explainable AI, which is already ongoing. Yeah, that's a good point.
Okay. So from my perspective as a submillimeter observer, I think the machine learning is really great if it can just make like higher resolution image from the single dish observation map that we have got. So like there are thousands of millions of SMG has been detected from whatever the South Pole telescope or the Scuba 2 from JCMT. But the resolution is pretty low, like it's around 10 or even higher, like 10 arc seconds, and it's very difficult to characterize its intrinsic properties like the sterilites or other things, and because we don't know the exact location of the SMGs, so we cannot just pinpoint to the real optical or the near infrared counterparts. So if we can have like the machine learning techniques like whatever to just produce a higher resolution image of this submillimeter map, it would be great. Like we can study them into the detail, and it's very challenging to give the current machine learning result with good fidelities, because we usually just use very generalized mock observations and as a training data set, and then to use it to get the high resolution image from the low resolution one. So it's really difficult to just to know how reliable this technique can be to get.
Right. So in this case, I guess the issues are both the training and the validation.
Yes.
Right. That's clear. There's one more comment.
So I feel like there's a whole lot of promise, and like Kurt mentioned, a lot of the onus of this comes in building constructive skepticism, where we question things the right way instead of just saying we don't believe this, and doing extensive validation to show that we both understand what models learn and that it's taking all sorts of systematics into account correctly. As methods, so ultimately, like I feel all of this is astrostatistics, right? Like machine learning is great, but machine learning, as talked about in the CS world, tends to ignore a lot of issues we run into in astronomy, which is like heteroscedastic noise and correlated measurement errors and aleatoric and epistemic uncertainties. All of these things are, fringe topics in the core ML literature, but very important to us. So I think the role of statistics is to sort of bridge that as we do the transfer from these like mixed density networks and things onto things like astronomical distributions, to be careful that we are folding all of these things in the right way. And I feel like the role of senior researchers especially is to question and ask for things that will make them trust what these methods are giving, and like reconcile that with their underlying physical intuition. And that will enormously help. Fields like cosmology and photoses and stuff are already doing like a whole bunch of ML, so like you don't even need to directly go to the CS literature. There's also like these intermediate pit stops where you can start getting things in. One sort of final thing was for the last point where you're talking about incorporating LLMs and stuff.
We'll go to that. Sorry if I interrupt you. We'll go to the second one now and then to the first.
I will come back.
All
right.
And you can come back to. Yeah. So I guess we can go to the second one. So who wants to comment or as some input on the second one, on really that more directly the usage of ML in combination with simulations or SAMs, perhaps to replace the traditional approaches. One example is, there are some efforts already ongoing in trying to use machine learning to complement or replace the traditional stack-grid methodology, or complement, the ability of running simulations at different scales and combining them. So I don't know if someone has comments or experience in that, or Phil.
So Sandy and we sort of briefly chatted on that specific topic, and I think the just sort of talked about the obvious challenges there are sort of what do you learn about the models and what can you infer in them, and also the extrapolation or the sort of out of domain challenges. I mean, the advantage nominally of these ML trained subgrid models is that they can utilize the high dimensionality of the data sets, but that also makes them exponentially more prone to out of domain stuff. But the other thing that I wanted to mention on this that wasn't explicitly in the question, but I was talking with Helen and others about earlier that I think is a complementary question is, that he's been thinking about is sort of, can we use ML models to gain more insight from existing simulations by trying to better understand, what are the key variables or processes that produce certain results? And, I think those of us who do these simulations know, as our simulations get more and more complicated, we were saying, we're more and more in this problem of, you see a phenomenology emerge, but then actually understanding what drove it or how it happened in the simulations. We had 4 talks about how disks form in our simulations that form disks, and we don't agree on that. So it's
so you think about using it more as a way to boost the interpretation of what we. That I think it's very important. There's someone in the back.
Hi. I guess from a slightly different perspective of, I think that using it as a way to kind of, extrapolate, but interpolate between different simulations is also kind of a interesting case for potential, because in those cases, if you're going between simulations, you have a very clear way of validating, at least to some extent. So like the way that I have approached this is looking at, looking at the power spectra between different levels of baryon feedback or different, cosmologies. And in those cases, your validation set is very clear compared to if you're, training on simulations applying to observations. And you're also just gaining a lot of, I guess you're going more, you're using it for speed rather than trying to learn some new information from it. And so interpretability is not quite as big of a factor. So I feel like that could be, that is an area for a lot of potential.
So this is more in the category of acceleration, in a sense, right? That's also not very important. And
I may make a comment myself. Obviously, I think in astrophysics is actually a bit harder, right, than in cosmology. It's arguably harder because we don't even know what the right parameters are, right? So it's so it's a kind of it's really a challenging problem, but it also means that there's lots of potential for everyone to do a lot of interesting work.
Does anyone have a comment on the emulation aspect, or has someone used ML already for emulating in simulations or in other types of models? Again, in cosmology, this is used a lot already since many years, but there are already efforts also in hydrodynamical simulations and in other aspects of astrophysical modeling.
We end up with garbage results all over the place. So how do we make sure that we're emulating the right data set, correct data set? The teacher data might be wrong.
Yeah, that's true. How do we define a ground truth? That's always the problem. In cosmology, it's not an issue or not as big as an issue, but for us it is. Yeah, that's.
Well, the challenge is actually that it's really hard to even get a single model that reproduces, let's say, a large, number of observations, right? We kind of struggle with this, right? In cosmology, the model is relatively simple, and so in lambda CDM at least, that you should find some set of parameters that matches it, right? But there's the model as a misspecification problem is definitely, I think, is a challenge for astrophysics and galaxy formation.
Maybe we can go to the third one, just in the interest of time. Who wants to say something about the third one? So the transfer of knowledge from other fields. Yeah, please.
So I just want to essentially do a quick plug here because we have started this collaboration called University BD that's sort of aimed at doing exactly this, where we are exploring the use of foundation models and LLMs and things in context of both doing like research problems within astrophysics, but also sort of meta, like how do you keep track of literature and things like that. So as part of this, we developed a tool called Pathfinder that basically uses LLMs to do literature reviews. So when you are searching for relevant papers, or when you're trying to answer specific questions and find citations for it, it helps to do that. It's coupled with ADS. We are developing this in partnership with them. And it just hit 100,000 users. So yeah, it's available at pfdr.app, and if people want to try it out, like, I think that might be helpful.
Any other comment on question number 3? Yes, Daisuke.
Thank you. We didn't have a chance to discuss this now, but I had a chat with during some of the lunches about this, and yeah, I guess it was somewhat unclear whether large language model is the right language for us who are solving partial differential equations and their evolution. So this idea that physics-informed machine learning, which is in principle is also capable of solving the partial differential equation, basically PDE and then putting all of those energy conservation equations into the cost functions, and then apparently in some of the other areas, like in medical science, where blood flow in some blood vessels, they can accelerate this kind of hydro calculation by several orders of magnitude. So that sounds very impressive. That if we, I know it's very difficult to implement this with physics and in our field, but nonetheless, the several orders of magnitude enhancement in PDE solvers, by basically effectively learning the structure of the equation and be able to predict and go faster, is a very attractive approach if we could somehow adapt it in our field.
Yes, I completely agree. And to add on what you just said, even the community of computational fluid dynamics is moving very fast in that direction. There are already several efforts basically doing turbulence using physics-informed neural networks. Yeah, that's, I don't know if someone has further comments. No more? I guess we are at a good time to end. So thanks to everyone, and yes, enjoy the lunch break now. Thank you.